All right, so I want to talk about three specific statistics tests that I've learned so far and how to compare them. So what I've learned so far, one was sloppy. I'm just gonna start right into it. The center. One, regression. Right. So regression is good for comparing. It compares the correlation between two data sets. Right. And put between two data sets. That's its job. Okay. So some information about how that happens. Basically, you take two data sets. Let's say you have set A and set B, whatever, and you plot them on a graph. Okay. So remember, there's some steps to it. You graph. Okay. At least in terms of if you're doing it on Excel, you graph it. You get your line. Okay. And the line has a slope. Mx plus b, where m is a slope and b is a y-intercept. Okay. From your slope, you can pull out a p-value. Get p-value. Okay. Now, mind you, the p-value is almost like I've just been starting to call it the prediction value. Okay. But basically, you get a p-value, and the p-value tells you if the sets are correlated. So remember, when the p-value is smaller than, bigger than 5%, bigger than 0.05, you cannot justify. This is how you have to say it in class. You have to say you cannot justify, all right, with confidence that there's a correlation. No confidence in correlation. No confidence to state correlation. That's kind of how you have to say. You can't say there is not one. That's not accurate to say as a statistician or just in the class. You have to basically say, I'm not confident that there is a correlation. That's really what you're saying, right? And then you have the p-value is smaller than 0.05. You can say that you are confident that there's a correlation. Basically, you're trying to say the two data sets are related. Like if I were to say, does eating high calories affect weight gain? You could compare, like literally, you take each subject and you say, how many calories do they eat? That's X. And then you say how heavy they are. That's Y. You compare that for like 500 people or whatever your sample size is. And now you can do the regression line, you can graph it, and you get your p-value. If your p-value for that set, I mean, we're expecting it to be smaller than 0.5, but let's say the p-value for that set were, we're talking about weight gain versus, I'll just do an example after I put this. So if it's smaller than 0.05, we'll say, we can say with confidence that there is a correlation. There is a correlation, right? And we can say that with confidence. That's the whole idea. And so we can say that. And so let me bring back to my example. Let's say we're talking calories versus weight gain. Right. So basically, you would have one axis versus another. And so I'll do calories on the X and then weight on the right. And you take a bunch of people. Boom, 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 boom. I assume it will look like that. And then you do your line. Okay. This line is going to come in the form y equals mx plus b. Okay. From your m, you pull your p-value. And so let's say your p equals like 0.0002. Right? Your p-value is much smaller than 0.05. And so you can say this 0.0002 is smaller than 0.05. And thus we can claim there is a correlation. Okay, there is a correlation. Then you want to talk about how strong that correlation is. Okay, if you want to talk about how strong that correlation is, you would pull out your R value. And so from there, you would go find R value. Okay, R or R squared, where if the, let's say you find your R squared, remember the bigger your value is, the better off you are, the closer it is to 1. Let's say we find R squared equals like 0.88%, like 0.88. And so basically we can say from this, as long as it's bigger than 0.85, we can say that they're very strongly correlated. Very strongly correlated. Okay. And so a lot of people kind of get that mixed up. The strength of the correlation versus the fact that is there a correlation? The p-test is going to say, are they related, right? Is there a correlation? The R value is going to tell you how strong the correlation is. So you have, is there a correlation versus how strong the correlation is? You can have there be a correlation. Like you can have a small p-value and then have it not actually be very strongly related. So what they're saying is when you're talking about how strongly the correlation is, that's just to say how much is it affecting it, you know? Is it to say that calories affect weight the most? Like does it affect weight a lot? or is it more, sugar intake affects weight a lot? And so you could compare the R value for both of those on weight. One of those is going to have a bigger effect on the weight, and the one that has the bigger effect on the weight is going to have the bigger R value. Does that make some sense? So they don't have to like match up with each other. So that's the R regression, It compares the correlation between two data. Set 2, confidence intervals. All right. And so we have you know what, let's do I'll do the T-test, T-test and Z-test, but we're just going to talk T-test. The T-test, it compares the averages of two sets, compares specifically the averages of two sets to the population, to their populations. So the averages of two sample sets, I want to give that detail, two samples, and abstracts them to the population. Okay, so what do I mean by that? So let's say we're talking weight gain versus, say we're talking weight gain versus the calories. So in this case, we're talking calories versus weight gain. Okay. Let's say the average calorie was 2,500, whatever. And then the average weight gain was, I don't know, 190. Sure. And so we want to see, based on our sample size, let's say we sample 300 people. Sure. Right. So based on our sample size, we see that the average of our sample size was 2,500 for the calories and 2,500 and 190 for the weight. And so we want to make the claim: is this is it the case that high calories equals high weight, or let's say low weight is like 170, right? And so do we want to say, when you want to compare the two, it's like, can I say that the more calories you eat, the more weight that you'll gain? So you want to compare these two guys, you're going to use the T-test to do that. And so the T-test, I'm assuming that you have to do like a Excel package, because I don't even know the equation. I just know I could put it in Excel and give me the answer. So when you want to compare these two to see if they compare to the population, because mind you, this is just a sample of 300 people, I want to see in general, that's the population. In general, is it the case of, more weight equals more calories or something like that, right? And so you do your T-test, and then you're going to get a p-value. The p-value is basically just going to be like your accuracy statement, and the same exact thing handles for the T-test versus for the regression. So if the p-value is bigger than 0.5, we can say that claim we can't be confident in a claim. So not confident in claim. And so the whole idea is that there's going to be a claim that's made. Someone's going to go, well, I claim that the more calories you eat, the more weight you gain, or whatever it may be, right? And so if you calculate the averages and you do the p-value, the T-test of those two sample averages, you can get a p-value of 0.05. You can say we're not confident in that claim, okay? And then another way to say that is you can't reject the null hypothesis. Can't reject the null hypothesis, because the null hypothesis is basically almost like the anti-statement. And so if you can't claim that they are different, right? Because that's what it's doing, is just trying to see if they're different or not. I'm saying I compare the average values of the samples, but that's basically saying, are they different? If you cannot get a p-test that says that they are different, then you cannot claim anything. And so from that, you have to say, I can't reject the null, which is to basically say, I can't not say that they're different. It's annoying, but that's the way it is. If your p-value is smaller than 0.05, and in a lot of cases 0.01, so 0.05, or smaller than 0.01 in a lot of cases, then you can say with confidence, in the specific percent confidence, the confidence percentage will be this number. It will be the p-value number cut out from 100. So let's say you get this, that's 5% confidence. And let's say you get that, that's 1% confidence, okay? And so we can say you can confidently claim, confident that there is a difference. Confident that there is a difference. Okay. And in the book case, you can say we're confident that we can reject the null. So confident within the percent value. So confident percent that we can reject the null. Okay. And so that's how that'll be presented. So that's the t-test. So mind you, you got two samples, regression. You could do a sample regression to see if they're related to each other and how well they're related to each other. Then you could t-test, which compares their averages to see if they're different. I'm not going to talk about, one-sided versus two-sided, okay? I just want to say the t-test tells you if they're different or not. The third one is a confidence interval, okay? So confidence interval. So the confidence interval takes one sample, right, one data set, instead of two. Everything we had before was two data sets, and it takes one data set and it compares it to a specific value, and compares to a specific value. It's similar to the t-test, but it's not. Okay. So basically it's like a lot of people see it as like a really specified t-test, but it's not a t-test. Okay. So an idea is like, let's say I was talking like nurse wages, right? Nurse, I think, yeah, I'll just talk like nurse wages. And we want to know if, let's say the average nurse wages was like 14,000, whatever. And we want to know does more school give you higher nurse wage? More school equals higher nurse wages? Okay. And so there's always going to be like a statement, like a question that's asked. And so we know that the average is 14,000, but we don't know, is it that more school gives you a higher nurse wage on average, right? And so basically I only have one data set, right? My nurse wage is a data set. So I'm going to compare the data set as school affects it. So we're talking the nurse wages as school affects it. That's still one data set. We're going to compare it to 14K. That's what the confidence interval does. And so there's a way to do that. Remember, the way to set that up, messing up my highlighters. Yellow for the highlighter, and I'm talking red for the pen. Cool. So first thing you do is you find the average of your set. So you find the average of your sample set. Okay. Because remind you, this average right here is a population average. So we're going to find the average of our sample set. Okay. And then from the average of our sample set, I probably should have talked about the average of the set on the t-test as well, but that's not important because that's more of a one-sided thing. So if you find the average of the sample set, then you find the confidence interval. Find the confidence interval. Now the confidence interval has to be given to a specific percent. So I'll say given to specific percent. Given to specific. And what do I mean by that? You can say you're 1% confident. You could say, and we're never going to have that. Typically, you're going to be 95% confident or higher. Okay. So mind you, remember how we had the p-value where 0.05 was 95%? That's going to be correlated to the alpha. So P basically becomes alpha for the confidence interval, where you want your alpha. It could be 0.05 for 95%. It could be 0.01 for 99%, or it could be 0.001 for 99%. So that's 95%. That's 99%. And this is 99.9%. Okay. So we're going to use our alpha. Basically, the confidence interval depends on three factors. You got your average, you got your alpha, and then you have your what was I think standard deviation? I can't remember. Shoot, I'll go get that later. But I'm gonna throw standard deviation. Pretty sure it's the standard deviation. And these are all of the sample. Okay, so I'm gonna put that in like a little orange. And so these are the sample, and sample, not the population. So from there, you'll be able to pull up a confidence interval. It's going to give you a range. Okay, so you're going to get your confidence interval is plus or minus some number. What you do to that number is you take it and you compare it to the average. Okay, so you get your average, the average that you had here. You say average plus or minus your confidence interval, and that's going to be your span. And what you do is you take the original number that we had. The average population was 14K. You're going to compare the population to this span right here. Okay. So let me put that in black and we say compare yellow black. And the last thing we do is compare population or the given value, okay, to the interval you get. So basically, let's say that this average right here, this interval, let's say my interval was like let's say it was 12,000 to, I don't know, 15,000. Okay. Well, the actual average that we're comparing it to is 14,000. And so because 14,000 actually exists inside of it, we cannot claim that the more math classes you have, the more your wage will be. Okay. And so you have your distance, your different situations. So you have, if it's within the range, then there is no difference. There is no difference. And a lot of time you can say we cannot claim that there is a difference. Okay, that's how you would say it. We cannot claim that there is a difference. Then you have, if it's above the average, we can claim that it's greater. Okay, so we can claim above. We can claim that it's greater. It is greater, right? And this is all depending on the situation that you have. And if it's less, it'll sit here. We can claim that it's less. Okay. Okay, so can claim that it's less. And so those are the three tests that I've come across, and knowing when to pick and choose between them, knowing when to do one versus the other. I'm gonna see if I can get some examples and then talk about the thought process behind why I would pick one test versus another. And that's going to be something that applies more to real life, because in real life people are just going to give you information and you're going to have to know which test you're going to use. Okay, and so just some data here that I came to terms with. One thing about the T-test really quickly, they're going to give you this statement, right? So they're going to go, I didn't even write up the statement, but the statement would have been for the T-test: can we claim that more calories equals more weight gain, right? And so, or actually that won't even be the statement. The statement is going to be given in a problem. It'll be like, this journal declares that more calories equals more weight gain. So it's going to be like a specific organization making a statement. They're going to say, this is what we believe. You're going to do the T-test, right? And what happens is you're going to have two different types of answers. You're going to have the statistical answer, and then you're going to have the conclusion. The statistical answer comes from just getting your p-test. So this right here, how we say we can't reject the null and we can reject the null, that is the statistical way of responding to that question. Then you're going to have the conclusion way. The conclusion way, and I wish I had some space. The conclusion way, it actually is just going to confirm or negate the statement made. So it confirm or negate original statement. So the statement was, the journal says that, this journal says that the more you eat, the blah, blah, blah. And so your conclusion will be, yes, the more you eat, the blah, 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 or we cannot conclude that the more you eat, the blah, blah, blah. And so that's how you would make it as a conclusion. It's always going to reference the statement, okay? And the statistical analysis is always going to reference the p-value. And so that's the difference between those, because that was actually giving me a huge hiccup. So knowing when to use the p-value as your statement, and they'll say, what's the statistical analysis or statistical representation? It'll come from just saying null hypothesis versus not null hypothesis. And then they'll say, what's your conclusion? Your conclusion is always going to come from your original statement. If they say a specific thing in the beginning, which they will, they'll say, this is what we believe. And then the conclusion will be to say, yes, this belief is true, versus you cannot say that this belief is true. Okay. It's not to say it's not. All you can say is that we can't confirm it. Okay. And so those are the three tests in a nutshell, without really any math, just more concept than anything. Because remember, at the end of the day, if you understand the concepts, then you'll be able to kind of steer your math. Okay. So hope this helped.